Hi, welcome to this introduction to logarithms. Before we get started, just a quick note to say that logarithms can be a little bit like the introduction to surds at GCSE, where it can be a really confusing topic to start with, but given the time, it can become second nature and just easy as surds are to you now. Logarithms can become similarly easy. So what is a logarithm? A logarithm is the power to which you raise the base. In this case, this base is b. So this is saying, what power do I need to raise b to get the answer a? And to make life a little easier, we're going to let that equal some letter. Let's say this equal x. I'm going to come back to this statement again. This is the power I need to raise b to get x. So let's rewrite that as an equivalent statement in terms of power. So the power that I need to raise b to get a. Okay, and x is that power. X is this whole statement here. Okay, so let's have a look at some examples, play around with this idea. So log b of 1. What power do I need to raise b to get 1? Well, anything to the power 0 is 1. So log b of 1 is the power I need to raise b to get 1. What about log b of 0? What power do I need to raise b to get 0? Well, if b is a positive number, or anything other than 0, there isn't an answer. So this is a kind of an odd one. I'm going to show you a couple of odd ones. There is no answer here. Okay, we can say, oops, undefined. Okay, and again, another similarly strange one. What about negatives? Okay, log b of -1, and actually instead of -1, just any negative. And actually, again, if you take b and you want to raise it to some power x, to get a negative answer, if b is positive, doesn't matter what number you put in x, it's never going to work. Okay, same here. So these two basically are undefined. They don't exist. Okay. All right. Okay, let's come back to a slightly more sensible one. Log z of z. What power do I have to raise z to get z? Let's write that down. Let's call this. What power do I have to raise z to get z? Well, z to the power 1 is z, so this must be 1. And what we're starting to do is sort of build up a picture of what logarithms are like. Okay. We know that logarithm of 1, so there's 1, gives us the answer 0. That's that point there. Log, let's say this is y equals log to the base 2 of x. So when x is equal to 2, then log 2 of 2 will just be 1. What power do I have to raise 2 to get 2? 1. So I'll put that value there. And then we keep going up. So if we have, let's say, 4, what power do I have to raise 2 to get 4? We're going to get the answer 2. And then 8 off the graph is going to be 3, and so on. And so what we do is we get a curve that looks a bit like this. Okay. Now this curve has some very similar properties to another curve that you may be familiar with, and that is the exponential graph. And so let's sketch that in here. Okay. So here this is y equals 2 to the x. Okay. Because as we said, every log statement can be written as an exponential statement. And so these two graphs are essentially the same except they are a reflection in y equals x. And any of you that know about functions will notice this means they're inverse functions. Okay, so let's crack on. Let's ask some more questions. Remember, a logarithm means the power I raise the base to get whatever's in my bracket. So in this case, log to the base a of a of x. What power do I have to raise a to get a of x? Well, in this case, hopefully it's relatively obvious. It's just x. This is saying what power do I have to raise a to get a to the x? Well, in this case, the question mark is x. Now, actually, this is a significant rule, separate rule that hopefully you're familiar with. That if you have two exponents, where the base is the same, then we know that the powers must be the same. Here, we know that the question mark must be there. Okay, and that's what we're using here. Here, let's have a look at this one, the next one. We're asking again, the power I should raise a, this says, the power I should raise a to get x. Okay, let's call it y. Let's say log a of x is equal to some value y. So y is the power that I raise a to get x. So that means here, if this thing here is y, a to the power y is x. So this is a to the power y must be equal to x. Okay. Now what I want you to notice here is the same idea about inverses. Notice I take x as the power of a to the x, and then I do the logarithm of that value, and I get back to x. Down here, if we do the logarithm base a of x, and then I raise a to that power, I get x. And so it's very similar to other inverse functions that we might be familiar with. So the square root of x and then squared, we know is x. Or similarly, x squared and then square rooted. We know they're just inverse functions. One is undoing the other. I'll do the same over here with sine. Inverse sine of x and then sine of it, well, that's just going to give us x. Inverse sine of sine of x, these things essentially just cancel each other out. It's a relatively simple way of thinking about it, but it works. And so we get the same property over here. Okay, log base a and a to the power of something are inverse functions. Notation. There's lots of different ways that logs can be written down. The one we're familiar with already is this, log to the base 2, so the little 2 is the base, and then the thing that we're trying to find, sorry, I should say it better, what power do we raise 2 to get x? Well, that's y. So here, what power do I raise 2 to get x? Well, that's y. Okay. But you may see logarithms written without a base. This means that, and whenever it's without a base, it's always assumed to just be base 10. Okay, so in this case, this is saying, what power do I raise 10 to get x? Okay, and the third one you might see is ln. This is natural logarithm, hence the n, ln. This is always base e. Okay, e. What's e? We'll get onto that in a moment. This is saying, what power do I have to raise e to get x? In this case, it's y. So e to the power y is x. So what's e? Well, you all know that pi is a number, 3.14159, something, and it's an irrational number. We can't write it down in its perfectly in decimal form. E is a similar number to that. It has a value close to 2.718281828. You might think that repeats as a pattern. It doesn't. It changes. It's all a bit like pi. And it has some really interesting properties that we can look into another time. Something that you might find really helpful, or you may already know, you can just type these things into your calculators when you've got all the values. So for example, if I wanted to work out what log to the base 7 of 3 is, type it in your calculator and it just gives you this value. It will be a rounded value in the same way a surd gives you a rounded value. This is much the same. So you now have everything you need to know to have a go at questions 1, 2, 6, 7, and 15 on exercise 7A. Have a go, see what we can do. Have fun.